And I'm live. That is pretty cool. Today is 23rd of January 2026, Friday. And let's just start solving. Okay, screen is stuck. Like, yeah, okay. Just shit. Yes, this might occur multiple times because this happens because uh, there is not a lot of free storage on my laptop, and I should have checked this before starting the stream, but okay. Yes, this happens because there is not a lot of free storage on the laptop, and somehow OBS uses storage to to stream. And if the stream gets stuck again, then I will delete a few files and make it work. Programming, 3D, competitive programming, and let's finish what we started. CP31, 1600 rated problems. Make them equal. I think we were doing this. I think no, we were not doing this. We'll see. Okay. D, make them equal. This is the problem that we are going to do now. Refresh. Nope, we haven't done any more of these. Handle, this is invalid. Please use a valid handle. Okay, because I changed my handle. Yes, that is also something. Can I change my handle? Yes, disconnect code forces and then connect code forces. Start verification, and yep, we can log in using code forces. And cool, all of the progress is lost. CP31 sheet. And yes, I should be audible. And hello, we are going to do CP31, this sheet. There are competitive programming problems in this sheet, and I started solving this in June. I think yes, June last year, and I reached till this point, and then I stopped for a few months. And yeah, let's just complete this whole sheet till 1900, or let's see how it goes. Make them equal. This is the question for today. And stopwatch. Okay. New vim here. Lazy update. Okay. Yep, this is the problem for the day, and very small. CP31. Yep. Okay. Hello, shit. Yes, it is raining. Where I live, it is raining right now. So yeah, we cannot fly kites even if we wanted to. Start the timer. Cool. You have an array of integers a of size, and initially all the elements of the array are equal to 1. You can perform the following operation. Choose uh, two integers I and x greater than 0, and I one of the elements index, and then increase the value of ai by this. Increase the value by this. Add this number. Initially everything is equal to this, and this is the lower limit, and x is greater than 0, so it can be 1, and initially all elements are equal to 1, so x can be 1, and these are like already 1, so 1 plus 1 ai would become 2 on the first operation. After performing all operations, you will receive ci coins for all such I that ai equals bi. Okay, your task is to determine the maximum number of coins that you can receive by performing no more than k operations. Okay, there are three variables here. Our initial array, our final array, b, and then the cost, the money that we will get. Okay, we have A array and we have our B array and we have our C array. Let's also make another array that would be called OP array, which gives us operations. And this OP array says if we have some element A0 and B0, how many operations it takes for us to change A0 to B0. That would be, let's say, OP0, and the number of coins that we will get after this would be, yeah, C0, and we have this for the whole array. Okay, so when we have found this, our best choice, would it be a greedy or non-greedy? Our final answer would be a set of elements, a set of elements from the original array A, such that their sum OP A, OP, B plus dot dot dot, all of them are smaller than equal to K, and the cost, that is CA plus CB for all these elements, is maximum. So we can use dynamic programming here. Yes, we can use dynamic programming here. This looks like knapsack. There is a cost. Shit, yes, this is knapsack. This is knapsack. There is a cost. Cost is this. There is a this profit or value that we get by choosing each element, and there is a total capacity, which is K. So yes, shit, this is knapsack. This is knapsack. Yep, 10 power 3 into 10 power 6, that is 10 power 9. So yes, at maximum we would have, at maximum we would have a knapsack table of 10 power 6 and 10 power 3, which is 10 big time complexity, 10 power 9, which is like 1 second, I think, and 10 power 9 we can do. Yeah, yeah, doesn't seem to be any problem with that. Hello, bro, I'm currently solving strings. I have done most 40 plus questions. Still each new question I solve, there is something new, like a new inbuilt method or new unknown logic. So I want solution. Is it okay? You can look at the solution if you can tell while you are solving a problem that you will not, whether you will be able to solve the problem or not. No, Meerut, whether you will be able to solve a problem or not. And if you know that you will not be able to solve a problem and you have given it enough time, then it is okay to look at the solution. But after looking at the solution, you should be able to do the question on your own and like write down what the things were, or figure out what the things were that you didn't know before solving the question, that you now know after looking at the solution, which are making you able to solve the question. Yep. And okay, so this is knapsack, and also here to make this OP array, we have to figure out how to make the OP array. Wait, shit, we do not have the C array. Okay, yes, we do not have the A array because all the elements are 1, N and K, the size of the array, and the maximum number, and then B, and then C. And okay, vector integer B, size and C in X, find B, replace C. Okay, I've taken the input, and here let's look at this, and how would we 1752. How would we solve something like this? 1752. Okay. 1752. So in the array, everything is 1 at the start. So this is already here. So number of operations would be 0 for this element. For this element, we need to go from 1 to 7. First, we have to choose x equal to 1 to make this one equal to 2. Okay, when we have 2, 7. The maximum amount by which we can increase this is 2. Yes, because we can choose x equal to 1, and yes, we will get 2. So we can make a 4 out of this, and target is 7. Then we need, so essentially we can, whatever we have, we can double it always, and at some point we would get to a number where if we were to double our number, we would exceed our target. At that point, how do we get 3 out of this? And x can only be an integer. Two integers. Okay, x can only be a integer. X can only be a integer. So if we 7, right, after 4 we can add 2 to this by choosing x equals 2, and 4 by 2 is 2. So we will add 2 and we will get 6. Now we need to add 1 to this, which we can do by choosing x equals to 6, and 6 by 6 is 1, plus 1, we do get 7. That took operations. We changed 1 to 2, then to 4, then to 6, then to 7. That took 1, 2, 3, 4 operations in total. But is there a better way? When we are increasing our number, initially when we are doubling our number, we are growing as fast as we can, and then we have to slow down our growth. If we added 1, then we added 2, then we added 2. When we have a number, if we choose x equals 1, 2, 3, 4, after 4 does not make sense. So we can choose, yeah, like we can add 4 by choosing x equals 1. We can add 2 by choosing x equals 2. We can add 1. If we add a big number like 10, then by we can use factors of that number. Those are the only things that we can add, the factors of that number. Yep. Okay. The factors of that number. We need to find a efficient function which we can use to find out the number of operations it takes to convert 1 to the target number in the array B. And here is the question. Yes, but like that does not mean I will stop doing competitive programming. I was like very afraid of competitive programming for the past few months, but yeah, I'm getting back to it now. And I have some projects like chess website which I want to make uh, after this month. Okay, we need a function which takes in a number like bi, and it gives us the minimum number of operations. let's use the algorithm where we are increasing, always doubling the number that we have, always doubling the number that we have till the point that if we were to double the number again, we would make it too big, bigger than the target. 8, 16, like that. And if our target is 7, let's see in this, these are our targets: 1, 7, 5, 2. So for 1, number of operations required is 0 because we already have 1. For 2, we also have a 2. For 2, number of operations is 1, just one operation from 1 to 2. For 5, the number of operations would be 1 to get to 2, then one more operation to get to 4, and then we can add 1, and yeah, in total 3 operations. And then for 7, we go from 1 to 2, one operation, then to 4, two operations. Then from 4 we can go to 6 by choosing x equals 2, and then from 6 we can go to 7. So that is 1, 2, 3, 4 operations. Okay, 1, 2, 5, 7. Cost is 0, 1, 3, 4, 0, 1, 3, 4, and the reward is this: 2652, 2652, but the order is changed: 1752, 1752. Okay, and the cost for these is for 1, 0, for 7, 4, for 5, cost is 3, for 2, cost is 1. We can remove these, and we can look at this as a knapsack problem now, where this this is the like reward price, uh, yeah, the profit, and this is the cost, the price we have to pay, and the total capacity is 4. Total capacity is 4, so we can make a knapsack like 0 elements, 1 element, 2 element, 3, 4. Total capacity is 4. We cannot use more than 4 operations. In which case, the best thing seems to be we can get this because this does not require, the cost is 0, so we will always get this number. And for 4 operation, we can use this and this. So our answer would be 9, should be 9, and it is 9, so that is good. That is good. That is good. So we will just use this algorithm for finding the cost, which increases, keeps increasing our number, keeps increasing our number, right? For a bigger number, let's look at a bigger number, bigger target number. For if we had a bigger target number, let's say 17, we can go up to 16 and then add 1. Yes. Okay, we can always go up to the highest power of 2 that is smaller than our target number. And the best way to get there is just by increasing the number, and going up to 16 takes 4 operations from 1 to 2 to 4 to 8, that is 3 operation, and to 16. 16 is 2 power 4. This takes 4 operations. Okay, and then depending on how much is there between 16 and the next power of 2, 32, we can have 1 till 15 as the difference, where if 1 is the difference, then we have 17, and if 15 is the difference, then we have 31. Now what would be the cost for 17? We just need one operation to get to 17. For 18, write it down. Specific, wait, let me also put it. 17. For 17, we just need one extra operation. For 18, also one extra operation we can add 2 by choosing x equals 8. For 19, we cannot do this in one operation. No, we cannot add 3. Okay, when difference is 1, this is what it takes. When difference is 2, when difference is 3, we must use 2 operations. When difference is 20, in this specific case, you can add 4 in just one operation. So there is no generic formula depending on the difference, like how much operations it requires. Wait, maybe there is. If 4 is the difference, then this, and if 21 is the difference, maybe if we write this in binary, 1 0 1 1. For 4, it is 1 0 0. For a difference of 5, we can go up. Yes, this takes 2 operations, 1 0 1, and shit, yes, it just depends on how many bits are on in the binary representation of the difference. Okay, because yes, because shit, wait, not just binary representation. If we had, yeah, shit, if we, if our target is 9, let's say, if our, wait, it does depend on binary representation. If our target is 9, then we can go up to 8 and then add 1. Okay, let's use this. I think this will work. Yes. So the cost, our function, which takes in bi, the target value, and tells us how much steps it takes to get from 1 to bi, would be the highest power of 2. Let's say 2 power some number x, highest power of 2, which is smaller than or equal to bi, right? X plus the number of zeros, which is like pop count, number of zeros in bi minus 2 power x. Pop count, therefore pop count of bi minus 2 power x. That is our cost. And bi is the only unknown here, and x you can just calculate at the time using bi. Okay, that is good. That is good. Okay. Vector int cost size n, size n. Okay. Int get cost takes in number x or bi, takes in a number bi, and x equals 0, and while 1 left shifted by x is smaller, 1 left shifted by x is smaller than bi, we will do x plus plus. If bi is 9, x 0, 1 left shifted by 0 is just 1, which is smaller, then increase it. Yes. No, x plus 1. Smallest value of x is this, and if we can increase x plus 1, less than or equal to. Yes. Yep. And how to get pop count in C++. Pop count in an integer built in. This only comes with GCC required bit. And we have pop count, pop head. Pop count is not there. We can use built-in pop count. Okay, let's use built-in pop count. What is the spelling? Built-in pop count for X. Not for X, but return pop count for pop count for one left shifted by X B I minus this plus X I equals 0, I is smaller than n I plus plus. Cost of the ith thing is get cost for B. Yes, get cost for BI, and let's just uh, print the cost for now. Okay, 0431 cost seems okay. Now, okay, now this is just standard knapsack problem. Vector of vector, which we can say dp bracket vector int vector int, and how many of these vector int, and internally this will have size w. I think this is how we get size. Make them equal. Yes, okay. W vector class template, and there should be, and we want dp I j would be best cost when using, best profit when using first I items with sack capacity j, with sack capacity j. W, what is W does not exist. K, no viable constructor or destructor. There was a short way to make a like two-dimensional array. Current rank is 1300. My J brain is kicking in and screaming to differentiate to find the point with zero slope. Wait, there is no slope. I should go back to study. Probably. Yes, I guess. I don't know. Bro, can you do post contest so we know how you approach contest question. Mm, yes, I think I can do that. I mean, today is a contest, and in tomorrow's stream, if there is like something you want to talk about, we can talk about that. That would be cool. Uh, Define 2D vector in C++ using, there is a specific thing, using class template automatic detection. Class template automatic detection. I think that is the name. Yes, class template argument detection, not automatic. Class template argument detection and vector matrix equals this, which is cool. So this should be working. I messed up the order, my bad. Wait, and format this. Okay. And say internally K, then I sap capacity and n plus 1, n plus 1 and K plus 1. Okay, and now the initialization step. Okay, 0. And now the initialization. And we also know that dp I j dp ij is maximum of dp I j. Either we do use this current item, which is I, or we do not. If we do not use this current item, then dp maximum of, if we do not use this, then dp I minus 1 j, I minus 1 j. But if we do use this, then dp I minus 1 bracket j minus cost of I, ci. Yes, and initially, yes, initially we have dp for 0, like the whole thing is 0 initially, so that is fine. For int I equals 1, I is smaller than equal to n I plus plus. And for each element, for int wk, w, let's say, w equals not 0, but we can move from the right. Yes, for int w equals k while w, we can use the current item, while w greater than or equal to cost of I minus 1 w plus plus minus minus. Yep, w minus minus. So we are going, if we were to like literally draw this, then we have items in this, like when we are not using any element, when we are using the first element, first two element, three elements, four elements, dot dot dot, till the, when we are using all the n elements and w, weight 0 1 2 3, at the end we have k. For each element we have two loops. Outer loop is going through element by element, and the inner loop is going from the higher weight till the weight w, where w is equal to greater than or equal to the cost of this current item that we are at. Because if w is smaller, then we won't be able to do this thing. Okay, therefore I dpi, here substitute j with w, dpi w equals maximum of dpi minus 1 W when we are not using the current item, or if we are using the current item, I minus 1 W minus, and also at this point plus uh, profit for the ith item, W minus cost 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 I minus 1, and also add to this profit, which is C bracket I minus 1, and output dp dot back dot back. Let's see. Okay, only the first one is wrong, everything else is correct. Why does it say 8? It does say 8. We are not, we are adding one less than the actual answer, and there is nothing which has a cost of 1. We are taking 6 plus 2, but we should be taking 7 plus 2. Right. Okay. Cost for 7 is 4. Cost for B7 for 6 is 4. Okay. Let's print this whole thing for auto x in dp. See how that's compile, run this. We just have one test case which has this 2. Okay. 0 0 0 0 is correct, but why do we have 1? Yes, because this one has 0 cost, so yes, cool. We can always use this. And when we are using first 2 items, wait, shit. Here answer should be not 0, non-zero. Okay, I get the problem. While w greater than equal to, not cost, but greater than equal to 0, and if w greater than equal to cost of I minus 1, then find this, otherwise else bp I w is just bp I minus 1 w, and now we should be good to go. 4 4 9. Cool. Run this, and cool, accepted. Let's see if this is correct. Submit. Yo, hello. Running 1600 rated, but okay. Okay. Wrong answer on test 2. Wrong answer on test 2. There could be the way that we are calculating cost could be wrong. Like this function which calculates cost, this might be wrong. Other than that, there does not anything else does not seem to be wrong. Everything seems cool apart from that. So, yes, apart from that, everything seems good. I starts at 1 and DP is already initialized. That is also good. And then we are going from higher weight to smaller weight, which is also fine. Yes, there is no problem with that. Answer wrong on test 2. And here I minus 1, always I minus 1, I minus 1. If we are not using the current item, then at the same weight, what is the best thing when we were not using this item? And what is the best weight? Best answer for when we were not using this item, when we were at I minus 1. And the capacity of our knapsack was W minus cost of using this item, I minus 1 item, plus C, that is the number of coins we get for using this. The only problem could be with this. uh, This algorithm is not correct, but it seems correct. Here we are finding X because we can always, from the array, we can always increase the number, double the number as much as we want, and we are doubling it. We keep doubling it till we until we get to a point that if we were to double the number again, then we would make that number bigger than the target. And when we do reach that point, we are calculating the number of operations depending on how much the difference is between the power of 2 that we are at and our target. Let's call that difference D, and we are taking the pop count of D, which is the number of ones in the binary representation of that number. For 5, which would be 1. But would there be a better, faster way to do this? Okay, what if we are at a number like 15? We will go to 8, right? And after 8, the difference is 7, which is 1, 1, 1. And 8 is 2 power 3. So 3 plus 3, 6 would be the cost using our formula. But is there a better way? For 15, we have 1. There really does not seem to be a better way. For 15, we have 1, then we will go to 2, then we will go to 4, then to 8, yes, and after 8, we need to add 7 somehow totally to this number. After 8, the greatest number that we can add, which is not 8, is 4, which is a factor of 8. So we can add 4 and we will get to 12. And when we are at 12, we need to add 3, which we can add in just one move by choosing x equals 4. We can add 3 and this does become 15. And this just took 1, 2, 3, 4, 5 operations instead of 6. Okay, so our formula is wrong. This function is wrong. Okay, because when we get to 12, our difference changes. When we are at 12, we can directly add 3 instead of adding 1 plus 2. We can add 3 directly. Yep, we can add 3 directly. So we need to find a way which is better. Your screen. Shit. Okay, yes, I thought this might happen. My bad. Oh. Okay, now it is good, and probably I should like delete something. Wait, desktop. Requiem for a Dream. This is a good movie. If you want some recommendation, this is a good movie. You should watch this. And yes, the screen gets stuck because there is not enough storage in the laptop, and I don't know how that works. But now this probably will not get stuck. Okay, we need to find a better function to find cost. Better way. To get to 15, it seems best to move from 1 to 2 to 4 to 8. There is like no other opinion in this. It seems best. But then we need to get to 12, then to 15. At every number, we can add any of its factors to itself. Yep, we can add 8. Uh, yes, we can add 8, 4, 2, or 1. Yep. Okay, we can add 8, 4, 2, or 1. Since we know that, okay, I think we can do this manually. After this point, when we have reached a point where if we were to double our number, we will exceed our target. If we have reached that point, I think we can just simulate the rest of the process, because at maximum, we are using a 32-bit integer. So at maximum, the max number of ones we can get is 32. So yeah, that is not a lot. And in each operation, we are at least adding one of these ones. So yeah, here when we are at 8, we need to add 7 to our answer, yeah, which is 111. Since we cannot add 8, we will add the next best thing, which is 4. But how do we know that? Okay, from for 8, we'll check if 7 is a factor. No, the biggest factors. How do we say that we are going to add 4 to this? What we need is, we know 7, we know 8. We need to find the biggest factor of 8, which is smaller than 7. And it is not very good if we were to just go from 1 to 2 to 3 till 8 and checking if this current number is a factor of 8, and if it divides this current number and the other factor which we get, if it is smaller than the target. That can take a lot of time. That can take a lot of time. Let's see, can it take a lot of time? What is the maximum value for k is 10 power 6? Maximum value for k is 10 power 6. So 10 power 10 power 6. So the difference maximum difference mm, when we are at a power of 2, we just know that all the factors which are like a smaller power of 2 are its factors and we can add them. But when after this we get to 12, we manually need to check for factors. There is no formula. For 1, we'll say that the factor is like, yes, the other part is 12. Okay, when we get to 8, we have 1, 2, 3. Let's say we check with 8, our target is 7. When we choose 1 as x, we will get 8, which is too big, so cut it. Then we choose 4, and then we choose 2 as the factor, and the other number that we get is 4, which is smaller than the difference, which is 7. So we do use this, and we get to 12. And now, since we have already added 4 to get to 7, remaining is 3. Then we do the same thing for 12. We have 1. If we were to use 1, we will add 12, which is bigger than 3, so we will not do that. If we choose 2, we will get 6, which is again bigger than 3. If we choose 3, we will add 4, which is also bigger than 3. If we choose 4, we will add 3, which is exactly this, and we can go directly to 15. But this part where we are going from one number to the next is not very good. Maybe we can do some pre-processing for this, and pre-processing using which we can find all the factors for a given number. I think there is a way to do that. All the factors for a given number. Shit, there was a algorithm to find all the factors for a given number. Yes, screen is not stuck now. There was an algorithm, I think. There is sieve of Eratosthenes. I think that is the pronunciation. There was another algorithm, I think, and it was something like for each number, for sieve of Eratosthenes, we have true or false. True if the number is prime, and false if it is not. But shit, there was an algorithm which we can use for finding the factors, and I think it was like 5, 6, 7, 8, 9. I think for each number we have its smallest prime factor. So for this we would have 3, for this we would have 2, for this we would have 7, for this 2, for this 5, 2, 3, 2, 1. And here, since this is the smallest factor, we can write out any number as any number, some number x, as a product of its factors, but we are not prime factorizing that number. We want all the factors. Yep. So for if we have 8, we would also need 4. For 8, we need 2, 4, and 8. Okay, let's say for 12. For 12, if we were to say, yes, the smallest prime factor is 2, all the factors of 12 are, not counting 1, all the factors are 2, 3, 4, 6, and then 12. These are the factors. Let's not even count 12. These are the factors. If we were to say from our list, the smallest prime factor of 12 is 2. That gives us 2, and 12 divided by 2, that gives us 6. So we know that one pair is 2 into 6. Now how do we know other pairs like 3 into 4? How do we get to that? Yep, this just gives us the prime factors, not. Yep, this is used for prime factorization. From 6 we can look at the smallest prime factor for 6, which is also 2, and we do 2 divided by 6, we get to 3, whose prime factor is 3 itself, and we have prime factorized the whole number 12 into its prime factors. So no, this is not very useful. Maybe we can go one by one, looking at each number. Okay, let's do go one by one and update this function here. It's okay. X, X, X is correct. That is like, yes, correct. And after X, let's have diff. Diff is bi minus 1 left shifted by x. While diff greater than 0, while there is a difference at each step, we know the current number. Okay, and let's also have current number 1 left shifted by x. We can say the current number here and here. Current number. Okay, so we need to find factors for current number. For int I equals 1 would not work. 2, I smaller than cur I plus plus cur, like Charlie Kirk. Okay, if I is a factor of current, for which we need to find the remainder, which is an expensive operation. If cur remainder I, if no remainder, then that means this is a factor, and if else we don't do anything. But if this is a factor, then cur divided by I, if cur divided by I is smaller than or equal to diff, then we will use this current number and we will say x plus plus increase the answer, the cost by 1, and diff is decreased by cur minus I, and current number plus equals current number divided by I. And also paid. And okay, here that divided by I smaller than equal to, so we don't have to check this. Okay, this seems good enough. Okay, that is taking a lot of time. Yes, that is taking a lot of time somehow. We are increasing diff, we are decreasing the diff and increasing current. Okay, this is just not working. Uh, let's compile, run for one test case 44, just this one. Okay, it is not working. See out, diff, compile. We have just one test case. It has two numbers and two, three. Let's say. Okay, we don't see anything even here. Diff greater than 0. Diff could be equal. Okay. And this should work. Let's just use the cost function in isolation and comment all of this out after taking this and this. Get cost when our target is 15. Comment this out also. Okay. Compile, run. It said 5, which is correct. Okay. And the only worry here is time complexity. Time complexity could be too high. Can we pre-compute like the number of operations needed for each number? Sure, I think we can do that. Number of operations for each number. Number of operations for each number. I think that would work. That would work. Let's see. Wrong answer. Okay. Not time complexity, but wrong answer. We shouldn't be getting wrong answer. Now, this function is also good, but we are getting wrong answer. Wrong answer should not be something that we are getting. There are no points of failure except from time complexity, where we can recompute, but we should not be getting wrong answer here. Wrong answer. If we are getting wrong answer, it means there might be something wrong with our main logic, main DP logic. We are taking n and k, n, the number of elements k, the total maximum capacity, total maximum capacity. Yes, we can do at most that much, that many operations, and we are taking b and c. Yes, b and c. B is the target and c is profit, and then we are updating the cost, and after that, and is for updating cost, get cost for getting to this target bi, and after that it is just basic Knapsack, initializing the knapsack, dp n plus 1, yes, where dp I j, let's substitute j with w, dp I w when is the best profit when using first I items with sack capacity, yes, sack capacity w, and we are going for I from 0 to n, both included, because this is n plus 1, so we can use n as an index, and vector for internal weight w ranges from 0 to k, because k plus 1 we can go till k, and okay, why do I have this as a comment here where literally this same line is in the code, but okay, fine. dp I w for any given cell in the dp table, the best answer would be if we do not use this number, if we do not use this current element, then what was the best cost at this weight when we were not using this element, and if we do use this element, then what was the best cost at weight c, at weight w minus cost of the ith item plus the profit that we get with this ith item, yes, which is correct, and which is exactly what we have done here. And it does not matter if we go from 0 to k or the other way around, while it's smaller than equal to k, and such, this does not matter, and w greater than if the current knapsack capacity allows us to use this cost for this ith item, then we will check we will update this dpiw value, otherwise we won't, otherwise we will just say what was the best cost when we were not using this item, and then dp back. There is literally no problem with this. Let's just submit this once more. Hopefully this just like maybe irrationally works, or we will look at the test case which is wrong, because this looks fine, this looks fine, and we are getting a wrong answer, not time complexity error, we are getting literally wrong answer. Like first we take out, yes, we do that, then we get from the number that will take n operations, and then check for remainder and keep doing till that remainder is 1 or 2, but that will be high complexity, I guess. This is what we are doing here. We are going till 2 power n, like 2 power x maximum, as much as we can increase by doubling the number, and then we have a current number and a difference. While there is some difference, we go by checking factors for the current number, which are like all the numbers we can add to the current number, and if the ith number that we are at, if that is a factor of this number that we are at, then yes, if it is a factor and use, and yes, this is like we can use this with the current difference. Yes, if we can use this with the current difference, then yeah, go with it. Increase the cost, decrease the difference, increase the current value, and break out of the loop and start looking again from I equals 2. We are not doing I equals 1 because we do not want to increase, we do not want to double the current number. Yes, we do not want to double the current number. Okay, on with the eighth number. 1, 2, 1. Shit, yes, this is 1, this is 2, second, third, fourth, fifth, sixth, seventh, and eighth. For this one, we are getting the wrong answer. We are getting wrong answer for this. See, we just have one test case, and this is the input, and that was too fast. 884, which is wrong somehow, and the best is 899. We can get better than 884. Let's output the cost. One test case, which is this, and cost is all of this, and we can use 91. Uh, but if you do DP and store operations for when remaining is 2 or 3 or 5 like that, then it will be fast when the remainder is this. But it does not solely depend on the remainder. It depends on two numbers, what the current number is and what the remainder is. If the remainder is, let's say, 3, and the current number is, let's say, 4, and we want to get to 7, then if the current number is 4, then it takes two operations, and if the current to get from 4 to 7 by getting to 6 first and then to 7. But if the current number is 12, then we can just go there in one chance, because 12 has 3 as a factor. We can always add the factor of the current number. So this takes one operation, this takes two operations. So this does not solely depend on the difference. This also depends. Yep, I think DP will be faster. DP, and should, the beauty of this problem, we are using DP for the overall structure, which is like, yes, which seems kind of obvious, but we are, you are saying we should also use DP for this smaller part of this whole function, which is just this, yeah, which is the part where we are calculating the cost. And this looks cool, where we do not have a single algorithm which we are applying. We have different algorithms for different parts of the problem, and we have here solved the major part, the big high level structure, but we are unable to figure out a cost function. But I think cost function here is correct. This one, cost, this might be slow, but this should not be wrong. But the problem is we are getting wrong answer, not slow but wrong, and it does not seem to me why this would be wrong, because we are literally doing everything here manually, Emmanuel. And we can even remove this. Wait, no, we can even remove this. Yes, we can even remove this, and here start from 1, and we would get the correct answer. Yep, we do get the correct answer. Maybe that was the thing, but no. Wrong answer does not make sense. Wrong answer does not make sense. And today is also a contest, so Yep, it will be cool. Yep, a wrong answer does not make sense. 884, 884. So, okay, this function seems correct. The cost function. So the problem must be with this, but this also seems correct. This is just standard knapsack, nothing special, where we are checking the cost. Maybe there is a difference between this and the knapsack. You have an array of integers a of size and initially all elements of the array are equal to 1. You can perform the following operation. Choose two integers I and x, then increase the value of ai by ai divided by x, that is make ai equal to ai plus ai by x. After performing all operations, you will receive ci coins for all such I such that ai equals bi. Your task is to determine the maximum number of coins that you can receive by performing no more than k operations. This is knapsack, where cost is the number of operations for every ai to make it equal to bi, and the total capacity is k, and the profit we get is ci. I think, yeah, and I do not want to look at the solution because, like, yes, we do understand the problem correctly. We also have a solution which should not have any flaw, but we have spent way too much time on this one. Let's look at the editorial. It is fine because nothing seems wrong with this. Okay, I do not want to look at the editorial. We will do this question later because this seems correct. Like, I cannot see any feasible problem with this apart from it being slow. Yep, right. Second, 2K. Let's wait. Shit, is it 2K? 2K, 2K rank. Let's go. 2K rank, or I thought you were saying subscribers, my bad. Preparing for ICPC or IOI or something? I'm new. I'm not preparing for anything. I'm just solving questions and like preparing for my brain to work better. And yeah, you said this is not working. We will do this question later on. So for now, it would be cool to move on to the next question. Casey is throwing a party, like literally throwing a party in someone's face. And one thing that I have noticed among these questions, it is that you might expect that more complex or algorithms are being used here, but uh, complex algorithms are not being used here. Instead, simpler algorithms are being used, but there are more than one algorithm in a problem. So, like, making them work together is the thing here for these questions, as I have seen. Okay, and yeah, make them equal. There does not, I cannot figure out. It would be easier to solve this if I had some idea where this is going wrong, but there is no idea where this might be going wrong. Everything seems perfect. This should ideally work, but we do not live in an ideal world. Okay, stopwatch for this question. Casey is throwing a party, and okay, I thought he wants everybody in the party to be happy. Very cool. He has n friends. His ith friend has I dolls. Okay. If you invite the ith friend to the party, he will be happy if only if at most AI people in the party are strictly only if AI people in the party are strictly richer than him, and if at most, okay, so we have a higher limit, AI people in the party are richer than him, and at most BI people are strictly poorer than him. Okay, Casey wants to invite as many people as possible. Find the maximum number of people he can invite to power 5. He can invite to the party so that everybody would be happy. Wait, both of them are upper limits. At most AI people are richer, and at most BI people are poorer than him. Okay, so for each person, look at this, uh, N and then AI and BI. N, AI, BI. Wait, why do we have three lists here? First line contains N. The ith of the lines contain two integers, AI and BI. Okay, okay, so the arrays have been given vertically, we could say. Okay, so we have 1 2 2 1 1 1 1 2 2 1 1 1 AI, A array, B array. Okay, and this one has one doll, this one has two dolls, this one has three dolls, and the currency we are using here is 3. Okay. Yep. Yes, 2K rating, my bad. Seems like, yes, struggle is real, palpable, but struggle is cool. Yeah. Okay, this guy, if we want to include this guy in our party, BI, there cannot be more than two people who are poorer than him. So we can have 0 people, 1, or 2 people who are poorer than him. But there are no people poorer than him. So yeah, so lower limit meets. But for AI, there cannot be more than one people who is richer than him, and there are two people who are richer than him. Okay, so if we do go forward with this person, then we can only choose one out of this or this. Okay, and when we can only choose one, then for this there can be at max one person who is poorer than him. So lower limit matches with our first choice being this person here, and the upper limit maximum 2, that also matches because there would be no one richer than him. Okay, so we can choose this person. Okay, answer would be 2. Answer would be 2, 2 people, because answer here would be 2 because it cannot be 3, because if it were 3 then we would have to choose this person also, and with this person we can only choose one of the other persons. So yeah, answer is 2 for this. 2. Generally speaking, if we do make a choice, that limits the number of people we can choose. Okay, for each person, for each ith person, there are two numbers, AI and BI, and AI maximum number of rich people richer, maximum number of people who are poorer, and there are total n people, and for this ith person there are for rich there are n minus I person who are richer than him, and there are I minus 1 person who are poorer than him. Right. So if we do go forward with this person for rich, this is the maximum choice we can make, and this is the available choice. And for poor, this is the maximum choice we can make, and this is the available choice. Okay. Yep. Maximum choice and available choice. Yes. And it does not seem like we can use DP. I think we can use DP. If we have a list where we know the answer for each of the um, ith person, if we know the answer till ith person, no, we cannot just add another person to this list, because adding another person would change the validity for each of the person, because they also have a upper limit to how many people can be on their right. Every number has a upper limit to their right and an upper limit to their left. Okay, so in a list of numbers in a list of numbers, every number, every ith number has a upper limit to numbers to its left and to the numbers on its right. Right. Okay. Upper limit. Okay. And this is 2 power 5. 2 power 5. This will use some sort of DP, but the answer mm, answer is like, we cannot also break this whole array into two parts and say ask what is the maximum number of people we can take from this, and what is the maximum number of people we can invite here, because the maximum number of people invited here depends on the maximum number of people invited here, and the maximum number of people invited here depends on the maximum number of people invited here. So yes, circular circular dependency. And also there is this cool thing, laser pointer here, which goes away. Yes, that is cool. uh dollars, shit, okay, my bad. uh Dollars. Okay. So yes, they are like normal human being then. They do not use dolls as their currency. Hmm. Answer for this thing depends on this. For this depends on this. And there are like examples are not very big. Uh, Small examples with n equals 3, 2, or 2. Here the limit is 0. So yeah, we will not invite this person. And yep. If there were like longer examples, that would have been cool, but okay. N can be 2 power 5. The thing that we do know is every number has a limit on left and a limit on right. How can that help us? And and a limit on right, left and right, left and right limit. Okay, let's go. Let's make a and a B array ourselves. 3 1 5 2 1 9 3, that is 1 2 3 4 5 6 7, and 4 3 7 5 6 1 2. Okay, and okay, so for 1 2 3 4 5 6 7, we will use blue for A. So for first, this can go left 3 numbers. There is like, but nothing on the left. For this can go till here. For this can go till here. We will take the minimum of this number or the first element, right? And for this can go 2 numbers to the left. For next one, this can only go 1. For next one, 9, this can go like all the way there. And for this one, it can go 3 elements to the left. Cool. And let's use red for B. 4 to the right, this much. This can go 3 to the right, same place. This can go 7 to the right, which is till the end. This can go 5, end. This can go 6, end. This can go 1, and this is already at the end. Okay, now we have to make our selection. We'll use laser for that. Selection. If we were to choose 4, we can choose 2 numbers from this. Wait, shit. Yeah, okay. Okay, there is something visually wrong with this. Having this thing go till 2 does not mean we can only choose 2 or 3. It means we can just choose 2 numbers on the left. Yes. Okay, so maybe this is not a very good depiction. Okay, for 1. Yeah, this is not a good depiction. Let's say for 1, in the left, it is just a dot. Then we have 1, and on the right, uh, on the right, if this has switched colors. On the left, if this, and on the right, this can go till 5, 4 more elements. So 1 2 3 4, let's say, right? Then for 2, we can go 2 elements to the left. For 3, we can go 1 2 2 elements to the left. For 4, we can go 2 elements to the left. For 5, we can go just 1 element to the left. For 6, we can go 1 2 3 5 elements to the left. And for 7, we can go 3 elements to the left. 3. Okay. And okay, 2 3 4 5 6 7. And right now I'm just trying to figure out a way to visually represent the problem. Maybe that will give us some hint. For red, for 1, to the right, we can go 4 elements, which we have already written. For 2, we can go 3 elements. 1 2 3. For 3, we can go till the end, which is 4 more elements. 1 2 3 4. For 4, we can go till the end, three more elements. One, two, three. For 5, we can go two more elements. For 6, one more element. For 7, just a dot. And does this help us in any way? I think we have to create a line here which touches maximum number of numbers, but it also depends on this right limit. Line. All are interlinked. Yes. Interlinked. Interlinked. Blade Runner. All are interlinked in a circular way. Circular or line. Left, right, everything interlinked. If you were to use a line for this, but that does not take into account how many things are on the right, like this could be very small, wouldn't matter. The final thing is we need to find a subset of these elements which works, and they have not given us a good example. Global round 17. And yes, mm, this is the problem. And we do understand the problem correctly. Kishi is throwing a party and he wants everybody in the party to be happy. He has n friends. His ith friend has I dollars. If you in dollars, not dolls, dollars. If you invite the ith friend to the party, he will be happy only if at most AI people in the party are strictly richer. Yeah, they didn't have to use the word strictly because no two people have the same amount of money. Strictly richer than him, and at most BI people are strictly poorer than him. Limits on left and right. Casey wants to invite as many people as possible, find the maximum number of people he can invite to the party so that every invited person would be happy. Let's use some sort of dynamic programming. Let's say we are at this element. There were 4 principles we have to use when solving a dynamic programming problem. They were in like Introduction to Algorithms, CLRS book. I don't remember them, but let's say this, what would the final solution look like? Let's find out the final solution. Brute force. One we can use, with one we can on the right use 4 numbers, right? Yes, let's write them. 4. For 2 use 3, for 3 we can use 4, for 4 we can use 3 numbers, for 5 2, for 6 1, for 7 0, and for 1 on the left we have 0 1 2 2 1 5 and 3. 6 seems to be something we can just choose. It does not matter. 6 we can choose because 6 works. 6 like does not matter if we choose all the elements here or all the elements to the right, we can always choose 6. So 6 is cool. Yep. 5 does not look cool because it limits our left range. So let's not include 5. 3 we can include. 3 actually we should include. 3 we should, yeah, we should include 3 because on the right we can choose 4 more numbers. So let's say we also use 3. Yes, we can use both of these, and this gives us a limit of 4 on the right. And we know we are not going to use 5. So yes, even if there was no limit, we would be able to choose all of these. So yes, that is something. So yeah, and 3 also does not disrupt anything. We can just choose 3. We can choose 2 and also 1. And then yes, 2 and 1. 2 and 1. Yes, that would be the answer, I think. 1, 2, 3, and 6. 1, 2, 3, and 6. 1, 2, 3, and 6. If we were to choose 7, then on the left, since we are choosing 6 and we are choosing 3 axiomatically because they look very good, then because choosing 3 and 6 are not limiting our ranges, so they are good. They are good numbers. And if we were to choose 7, then we would only be able to choose one more number from 1 to 5. So we should not choose 7. So this answer would be equally correct as this, because we would choose 7 and then we would choose like 1 or 2 from here. So we would also have 4 elements there: 1, 3, 6, 7. Okay, and this seems good. Now a property which it holds is, for 1 on the left we have 0, and on the right we had the limit 4, which is fulfilled. For 2 we had 1 and 3. Okay, for 3 we had on the left limit, wait, shade, for 3 we have on the left we have limit 5. So but yeah, 2 also works. 2, because we cannot choose any more elements than 2. 2, and on the right we have 4, and for 6 we had the limit on the right 1 and on the left 5, and these limits are satisfied. I think we can choose one more number here. No, we cannot choose one more number here. Either we go with 4 or we go with 5. If we go with 5, we won't be able to choose any of these numbers. We would only be able to choose one number. And if we were to go with 4, then yeah, we already have 3 numbers here. So yeah, that does not work. So this is the best answer, one of the best answers. And the property that it holds is this. So if we take away one of these person, we still have a correct answer, valid answer. It might not be the best, but it is still valid. Everyone would still be happy. Removing someone does not change anything, but adding someone does change things. But what does that tell us? That does not tell us anything. If this is our correct solution, we can take away numbers and it still works. It still works. Okay, there are now two ways. Either we can begin from a empty list and keep adding numbers to this and finally get to the correct solution, or we can begin at a wrong solution which includes all the numbers from 1 to 7 and repeatedly remove numbers from this and slowly get to this solution, like bottom up or top down, I think we can call them. But how do we decide which number to add? We cannot go left to right because mm, when choosing a number, if we only have knowledge about the left, we also need to know things from the right. And the time complexity of the algorithm would be somewhat like n log n. And I think it will turn out that there is a this is a sort of standard problem, which is a standard problem. Maybe 1236. Yes, so we cannot know if adding this current number works or not, because we might in the future add more numbers. But when we have all of the numbers in our list, we can know which number does not work right now. So if we had a list 1, 2, 3, 4, 5, 6, 7, we know 7 does not work. 7 does not work, but should we just remove it? Maybe 7 would start working if we remove everything else. And 7 would start working, but right now it does not work. So why? And there are a couple of numbers which do not work. This does not work. Okay, right now we know that 7 does not work, 6 does work, 3 also works, and everything else does not work. Only 6 and 3 work. So yeah, I think we can just add 6 and 3 to our final answer. 6 and 3. Now what? We have an option to keep to remove one of these and keep to remove one of these and keep the rest, and then see which one does not work in the next step after removing one element. But even if we somehow figure it out, and the time complexity would not work, because figuring out which numbers work and do not work at a certain step will require us to go through all the numbers. And yeah, so n and removing numbers would also be n, like, yeah, time complexity would not work, it would be n square. Yep. Shit. Okay. Left limit, right limit. We'll think about this for like 10 or 10 more minutes, and then we will look at the solution, because yeah, there is no point in wasting time when we can look at the solution. And also we are going through we are exhausting our space of thinking. So yeah, it is fine to look at the solution after 10 more minutes. And let me go to the washroom, and I will be right back in 1 minute. I'm back. Everything is so interlinked here. Everything. Yes. Mm, Choosing one number changes everything. Left and right. Yes. Well, let's try to force dynamic programming on this. Yes, let's say we only have one in our list, in which case answer would be one. When we have the first two numbers, one and two, we can choose both of them. So that also works. Okay. No, no, no. If we have one, let's say somehow we know what the correct answer for what the best answer for all the numbers from 1 to 5 is and then we are deciding whether to add the sixth number or not. For sixth number on the left the sixth number, okay, yes, we can add the sixth number to this if uh, the left range of 6 matches with how many numbers we have in our list, and the best answer from 1 to 5, let's say, is 1 and 2 when we are only choosing 1 and 2, and the left limit for 6 is 5, so which is certainly in the limit, so we can say best answer is 1 to 6. So this, from 6's point of view, we can add it to the list, but from the numbers which are already in this list, from their point of view, there is a way we can there is a way we can like keep track of how many more numbers we can add on the right, which is just looking at whenever we add a new number, we will have a current mm, range, right? And when we are moving, adding one more number, whenever we add one more number, we will reduce that by one, and we will take the minimum of that and the minimum and the right value, the right range of the number that we have just added. So yes, like bi for this number. But how do we decide if we should skip a number? Because we would certainly add 3 to our answer. 1 2 3, and then I think we would even add 4 to our answer. No, we would not add 4 because we cannot add 4. We cannot add 5 because of the left limit. Let's say 4 had a left range of 3 and a right range of just 1. Right range, let's say, of 0. So if we were to add 4 to our answer, when we already had 1, 2 and 3, for 4 the left range is 3 and the right range is 0, which works, and the current minimum number of the current right range is, let's say, 2. Current right range, let's just say, is 2. Then this works. We can add 4 because we are just adding one element and the current range is greater than 1, so that works. And also 4 can have at most 3 numbers on the left, and there are just 3 numbers, exactly 3, so we can add 4. But then we move on to 5. We cannot add 5 because we won't be able to add anything on the right because this is 0. But we would be able to add things if, let's say, we hadn't chosen 4 here, and let's say 6 and 7 both were numbers. 6 had a left range of 5 and 7 had a left range of 6, and 6 has a right range of 5 and 7 had a right range of 0. So if we hadn't chosen 4 at this point, we would have had a better answer, which would have been 1, 2, 3, 6, 7, which we missed by choosing 4 here just because 4 was valid. So how do we know that 4 is a valid choice? We do not know. Backtracking? Does this require backtracking or something like that? Okay, for each number, either we do have it in our list or we do not have it in our list, where the total space of solutions becomes 2 power n, because every ith integer can be chosen in the list or cannot be chosen. So yeah, two possibilities for each number, therefore 2 power n total solutions, and that certainly is like never a good idea. So is there some information which we can keep track of beforehand which helps us narrow down this solution to some better solution? 127, 127. 2 power n, yes, total number of solutions. And from a correct solution, we can always remove a number and it is still a correct solution, but just not the best solution, but still a valid one. But we cannot add more numbers to that solution, to that valid solution. We can like raw dog this thing by generating all of the solution, all of the valid solutions. Yes, by generating all of the valid solutions and checking out the one which has the maximum number of elements in it, and yes, but that is like not very good. Let's just for fun, since there are not a lot of numbers in this example, let's use our brute force just for fun. N and K. No, just N. What would K even mean? Okay. Take an N and vector int a n and bn for int reference x in a, c in x, b. Okay, and shit, that is not how we take an input. For int I equals 0, I smaller than n, I plus c in ai, bi, or left and right makes more sense. Left and right. Right, and yes, let's make a bit set of size n, but we cannot give a dynamic size n bit set. Let's use a vector of boolean, but that is not very good. Let's use a bit set of size 1e6 bs, or set yes, set. Okay, we will say st equals 0. Can we do that? We can do that. And we will say while st is smaller, while st is smaller than 1 left shifted by n, which in itself is big number. Okay, let's use an integer instead of this. We do not have a very big test case. Int st equals 0. Right. Okay. St in its binary form is telling us which numbers we are, which people we are inviting and which people we are not inviting, and we now have to check is this a valid solution or not, and update our maximum solution if this is a valid solution. So for valid, let's use bool is valid. This takes in integer st, and this takes in vector int reference l and vector int reference r, and tells if this is valid or not. Okay, for int I equals 0, I is smaller than size, no, I is smaller than, let's say, 32 plus I plus int cl current members on the left is 0, current members on the left is 0, and int maximum members on the right is infinity, or 1e9, let's say. Now if current member on the left is greater than what the current value on the left can be, which is L, should, if this ith bit is on, if st and bitwise and with one left shifted by I, if this bit is on, then we are using this thing, and if current left is greater than left limit for this ith person, then return false. So otherwise, then left limit matches, and we will say current left plus plus, and also we have to check the right limit for this. Yes, if maximum limit on the right equals 0, then also yes, so there are two conditions here of this, or MR or not MR, then in both the cases return false. And then update CL and update MR. MR equals minimum of MR, or right for this I number. And if we do pass all this, return true at the end. Is valid, works. Okay. If is valid, ST, L and R, then MX equals maximum of MX or built-in built-in pop count for ST. See out MX, this will work, but this will fail for the solutions. Okay, this is shape ST plus plus. Wrong is crazy. This is left limit and this is right limit. No, the first number is AI. AI is how many people are richer, which is the right limit, and the second number is BI, which is the count of people who are poorer, which is the left limit. This works here, but the time complexity is way too much. Not just way too much, this will not work because ST is just 32 bits. Wrong answer, certainly. Hello, thank you as Astro with our, and all the best to you too. Let's like do the best thing. Okay, it is somehow still running. Yeah, we will get time limit exceeded error. Wrong answer. Wrong answer. Wrong answer is crazy. Wrong answer because we are not going after this ST point. So yes, wrong answer. Let's look at the solution now. It is fine. Question number C and global round this. Hints. Okay, hint one. Let ans be the answer for any I smaller than ans. It is possible to in Boolean search. Wait, shit. Is this, does this require Boolean binary search? We certainly know that the lower limit L is 0 and the upper limit we do not know. Uh, we can just say upper limit is, let's say, n or n plus 1 if you want to say that our answer lies in the range L to R. L included, R is not included. Then yes, L is 0, R is this. Now can we know using something that M is a valid answer? M is a valid answer. Can we know that? Can we know M for some number M if it is a valid answer or not? We can take We can go through all of the elements. That is fine. We can use O of n time to determine if a certain number m is a valid answer. Can we do that? That would be binary search. For a certain number m, can we use that? Okay. In our earlier solution 1, 2, 3 and 6, let's say m is 5. M is 5. Let's rewrite this whole thing here. If we had 1, 2, 3, 4, 5, 6, 7, left limits are 3, 1, left limit is b and right limit is a. 3, 1, 5, 2, 1, 9, 3, and right limits are 4, 3, 7, 5, 6, 1, 2. And here we are asking whether 5 is a valid answer or not. Let's use laser pointer, or using K we can go to laser pointer, or F for frame tool. K does not work. I can stop Vimium exclude keys. Yep. Let's see. K work now. Yep, K works. K, yes. So yeah, 5 is 5 a valid answer ever? If this number was included in the final answer, this would, okay. If this was included, then we would need the sum of left and right to be 5. Here the sum of left and right is greater than 5, so that works. Here the sum of 1 plus this plus 1 for including this number, that is 5, so that works. Here sum is also 5 or greater than 5, so that also works. Here not just the sum, but we cannot take these numbers as they are. We have to take this number or the minimum of how many numbers there are on the left. So let's replace these values with them. Okay, so 0, 0, and here 1 works, 1 works. 5, instead of 5 we should use 2 here, instead of 4 1 is okay, and instead of 9 we'll use 5 here, and 3 also works here. For the right limits, 4, 3, 7, instead of 7 we'll use 4, and instead of 5 we will use 3, and instead of 6 here we will use 2, 1 and 0. Okay, now laser pointer, sum of 0 plus 4 plus 1 is 5, so cool. Sum of 1 plus 1 plus 3 is 5, cool. Sum of 2 plus 1 plus 4 is greater than 5, that also works. So we have, let's say we will also keep a counter of how many numbers we have already seen. So we have seen till now 3 numbers for which 5 works. Then we see 4 does not work. We see 5 does not work. We see 6 works. So 4 and 7 does not work. Shit. I think that is how it will work. Hello, it is going cool, I think. And after 55 minutes and looking at a hint, I think we can do this. We can do this. We can do this using binary search. Using binary search for a given number m, we need to figure out whether m is a valid answer or not, and we can do that by going through the array and looking at how many numbers we can choose. Okay, shit. Shit. No, 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 no. This will fail. This will fail. This will fail. This will fail. If we had the distribution like 1, 1, 6, 1, 2, 6, and 3, 1, 6, and so on for like till 7, 1, 6. All of these. Wait, this would be 0. This would be 1. Yeah. This would be 5. Let's say this. Yeah, this would be 6. And we are looking for if 7 is the answer or not. This would be this would be 5, and this would be 4. For 5 we would have here 3 for 6, 1, 1 and 0 and 1. Okay, shit, this might actually work. This might actually. One, 2, 3, 4, 5, 6. Let's see if this works. Let's see if this works. Okay, remove everything and take in n vector in left size n and right size n for n I equals 0, I is smaller than n I plus plus. C in first number is right and Li and left equals 0 and right equals n plus 1, and while right minus left greater than 1 and n equals left plus right minus left divided by 2, and we will have a function called is valid, which returns a bool. It takes in number m and it takes in vector integer reference L and vector integer reference for right. And after this we will call if is valid m l r l equals m, left equals m, else right equals m at the end. See out left return true for and I equals 0, I is smaller than n I plus plus, and n equals L dot size. That works. And m if at any point minimum of I plus L I comma L I plus minimum of, on the right we have n minus I minus 1 left elements, left on the right, and the range, which would be Ri plus 1. If this number is greater than or equal to n, then and also count equals 0, count plus 1, and then return count greater than equal to m. Let's see, it will work here. Let's see if it works generally speaking. Time complexity is fine. This might just give wrong. Okay, for the second one we had out of bounds. Okay, wrong answer, wrong answer. Yes. Let's look at the rest of the hint, or maybe, yeah, this just does not feel good. Hmm, this does not feel complete. Is there another way of checking if M is the correct answer or not? If Boolean search is, if binary search is the way to go. Let's look at the tutorial. It is going cool. Hint 1. Okay, we just read first line before. Let answer be the answer for any I small. It is possible to invite exactly I people, and for any I greater than answer, it is not possible to invite exactly I people, because removing one person from the party doesn't make anyone unhappy. So if we invite all of these people, we can invite all the people except the last one. Yes. We use binary search to find the maximum I, that is that it's possible to invite exactly I people. Assume we want to invite X people. If there are I people poorer than we, there are X minus 1 minus I. There are I minus 1 people poorer than a person V. This many people richer than him. If I smaller than BV, for the like Vth person. And what is X here? Assume if you want to invite X people, if you want to invite X people, if there are I people poorer than V, then V who is some current person, then there are X minus 1 minus I people. Not that there are, there must be this many people richer than him. And if I is than smaller than or equal to BV, and and I is smaller than equal to BV, and X minus I is the number of person we are saying we want on the left. On what metric? There are going to be V minus 1 people. We can say remove just, we can just remove V. Yes. I is the index of the person. Yes, we can use I as the index of the person. I as the index. Then I has to be smaller. I is the index of the person, and there are I people who are poorer. Then we should be able to choose BV. Okay. And I should be greater than X1. AV should be greater than the number of people we want to choose on the right. Okay, if you want to choose I people on the left, and then we would be choosing x minus 1 minus I people on the right. Then the number of people that we choose on the left should be smaller than the number of people we can choose for some person, and on the right it should be smaller than the number of people then we can choose on the right. But how are we deciding on I seems just random here. And then we are combining okay, let's say we are at some person I. For that person we are choosing L people on the left, and we are checking whether M is the correct answer or not. If we have chosen L person on the left, then on the right we need to choose M minus 1 M minus 1 minus L people on the right. Yes, we have to choose M minus 1 minus L people on the right. And there should be two things: the number of people we can choose on the left is let's say bi, and we are saying bi is minimum of the original value of bi and I. Yes, cool. And we are also saying ai is the minimum value of the original ai, or n minus I minus 1. With that, we can choose this many people on the left and this many people on the right. So our choice L, which is arbitrary, does not matter, it is just a random thing. Bi should be greater than equal to L, and ai should be greater than equal to M minus 1 minus L. And let's join these two on L. So bi greater than equal to L, and for this thing we can say ai is negative, then plus M minus I greater than equal to L. No, smaller than equal to L, because we changed signs. So we have an upper limit for L and a lower limit for L. Lower limit is M minus 1 minus AI. L should be greater than equal to this and smaller than BI. And L is arbitrary. Like L can be anything, does not matter. And for, let's say, for some random number, if we have made the choice L, then for some number on the right, okay, L initially we can say is going to be a range. L can be anything from 0 to, but yes, shit, no. How do you decide which numbers to add and which numbers not to add? Yes. Shit, let's look at the actual solution. This still does not Wait, no, I do not want to look at the solution. I want to figure it out on my own. And yeah, I guess, yeah, today I haven't been able to solve any questions, but that is fine. That is fine. I have like, today is a contest, and also we were not sitting idle. We were thinking for 2.5 hours straight. So that is a good thing. And today is also a contest, so I would be solving questions then also. And I guess for today, this would be it. We haven't solved any question today, but that is fine. No problem with that. Yeah, we were just thinking. So yeah, cool. And this would be it for today. That would be the end of today's stream. And thank you for being here. Today is a contest, and tomorrow we will solve more questions, or at least one question. Yep. Thank you for being here. Bye.